Hi guys, so today we're doing lesson 6.3, which is the last lesson in chapter 6. We are now talking about how do we solve systems of linear equations with 3 variables. So the last couple of lessons we've just been doing systems of equations with 2 variables. Now it's going to get a little bit more complicated and a little bit more fun. Okay, so for the warm up here, we've got a system of equations that we're going to solve using elimination method, which is the last method that we talked about. Now, when I look to see if I have one of my variables that will automatically eliminate, I don't, because I have a 5x and a 2x, a 3y, and a negative 4y. So I also try to evaluate, okay, can I just multiply one of the equations by one number to get from, let's say, this 2 to a 5, or to get from 3 to a 4? I cannot unless I use decimals. So this is going to be one of those instances where I multiply both equations by a number. So let's just take a look at the 3 and the 4, for instance, because those are a little bit smaller than the 5. So if I try to get my y's to eliminate, the nice thing is that one of them is already a negative and one of them is a positive. So if I want to get the 3 and the 4 to match, I would multiply each by the opposite and get to 12. So I'm going to multiply this top equation by 4 and the bottom one by 3. Then I'm going to write this over here, so distribute everything. I get 20x plus 12y equals 36. And then distribute the 3 down here. I get 6x minus 12y equals 14 times 3 is 42. So now I have 12y and a negative 12y, which are going to eliminate. I add the equations together. 20x plus 6x gives me the 26x, and then 36 plus 42 gives me a 78. Divide both sides by 26, I get x equals 3. So my first variable solved for, and then now I'm going to plug this back into one of the original equations. I'm going to plug it in here for the second one. Actually, let me just draw this over here, and I'll get rid of all these, just because this looks a little bit less messy. So we get 2 times x, which is 3 in this case, minus 4y equals 14. Okay, 2 times 3 is 6. I'm going to subtract that from both sides. So I get negative 4y equals 8. Divide both sides by a negative 4, and I get y equals negative 2. So I've solved for both of my variables. I write my answer as a point of intersection. So 3, whoopsies, negative 2. Okay, and then the last question on the warm-up is, what do we call the solution to a system of linear equations? We call it a point of intersection. And that goes back to when we look at the graph, what does that look like on the xy coordinate or plane? It is where the two equations intersect or overlap, and where those solutions then satisfy both equations. Okay, so we obviously, up until this point, have mostly talked about two-dimensional graphing in college algebra. However, we live in a 3D world, and so there is such a thing as three-dimensional graphing, which you will start to get exposed to in higher-level math classes. We're not going to do 3D graphing today, but I want you guys to see how this looks when you have an x-axis, a y-axis, like we're used to, and then you also have this third axis or third dimension, which is the z-axis, okay? So when we graph in 3D, we actually have coordinate points that have an x, a y, and a z coordinate. And you're gonna see in today's examples, when we're using equations or systems of equations with 3 variables, we're gonna end up with solutions here that have x, y's, and z's. Again, you don't have to worry about what this actually looks like graphically, but this kind of just shows you a very, very basic intro to that. Okay, so in general, any equation of this format, ax plus by plus cz equals some constant d right here, where a, b, c, and d are all just real numbers, okay? And a, b, and c, those are the coefficients in front of my variables. This we still consider a linear equation, but now it has 3 variables, our x, our y, and our z right here. Okay, so that's what most of our equations are going to look like today. And when we solve for these equations with three variables, the solution, instead of being an ordered pair, it's going to be an ordered triple. So meaning we're going to have an x value, a y value, and a z value, just like we talked about on the previous page. Okay, so an ordered triple because we have all three values. All right, so first, before we actually fully dive in, let's just talk about whether or not an ordered triple actually satisfies a system of three equations with three variables. Okay, so we'll look at this example. We have the ordered triple -1, comma, -4, comma, 5. So -1 is representing x, -4 is representing y, and then 5 is representing z. If we want to test to see, is it actually a solution to this system of three equations that I have here, what I need to do is I need to plug in the -1 for all of my x's, the -4 for all of my y's, and the 5 for all of my z's. And then see, do I actually get the left side of the equation to match the right side? And if it does for all three equations, if that ordered triple satisfies every single one, then it is in fact a solution. If it does not, even if it works for two of the equations but not the third one, it is not a solution to the entire system, because when we say it's a solution to the system, that includes all three equations. Okay, so I'm just going to write them over to the right here, and I'm going to label them equations 1, 2, and 3. Okay, so equation 1 here, let's go ahead and plug in our values. So -1 times, or -2 times -4 plus 3 times 5 equals 22. I'm going to put a question mark over that just to verify, because we're not 100% sure yet. That's what we're testing to see, does this actually give us 22 when we plug this in for x, y, and z? So we're just going to simplify the left side, because obviously the right side is already simplified as much as possible. So I have -1, -2 times -4, this becomes 8, 3 times 5 becomes 15. I'm going to still see, does this in fact equal 22? So -1 plus 8 is 7, 7 plus 15 is 22. So yep, this one checks out. 22 I get on the left side, I also get on the right side. So this one does work for this specific equation. All right, let's check equation number 2. So 2 times x minus 3 times y minus z, does that in fact equal 5? And again, I'll color coordinate here for you guys just to see my x, my y, my z. So again, we're going to simplify the left side. I get -2 plus 12 minus 5. -2 plus 12 is 10, and 10 minus 5 is 5. And 5 does in fact equal 5. So the second equation also works, or this ordered triple is in fact a solution to the second equation. Okay, last but not least, let's test the third equation. So 3 times x plus y minus 5 times z, does that in fact equal -32? Again, here's my x, here's my y, here's my z. Okay, so I get -3 minus 4 minus 25. -3 minus 4 is -7, and -7 minus 25 is in fact -32. So the left and the right side do match. And then therefore, this tells us that yes, in fact, -1, -4, comma 5, that is a solution to this system of three variables, or three equations with three variables. Okay, so we just verified this. That's all that this slide tells us here. All right, so here are the steps to actually solve for a linear equation or system of linear equations with three variables. This is definitely going to be more complicated than what we've done in the last couple of lessons, so just kind of hang tight. And I know that these steps are a little bit long, so feel free, you can abbreviate them for sure. So step number 1, we need to reduce the system to two equations with two variables. We know how to solve systems of two equations with two variables. So the way that this is done is usually by taking two different pairs of equations and using the addition method of elimination to eliminate the same variable from both pairs of those equations. Okay, so you want to either decide, I'm going to eliminate x, y, or z, and you'll do that with two different pairs of equations. Step number 2, when you have two equations now with just two variables, so you've eliminated one of them, then you can solve the resulting system of two equations. And you do that using, addition for elimination or substitution method. So that we're going to be familiar with. Okay, the result of that should give you the value of one of your variables. So you should end up solving for x, for y, or for z. Once you've done that, step number 3 is to back substitute, which just means you now take that variable, you plug it back in for the value in the variable from step number 2. So you go back to one of your equations, and again, this will all make a little bit more sense when we do examples. You'll plug it back in to one of the two equations that just have two variables in them, and then you'll find the value of the second variable. So you may have found x in the first one, and then you'll find y or z. Step number 4, now that you have two of the variables solved for, you will take both of those variables and the values that you found for them and plug them in or back substitute them into one of the original equations to find the value of the third variable. And then step number 5, like we just did in the previous example, you can check the proposed solution in each of the original equations just to make sure you did it correctly. And I'd say this step, we're not always going to ask you to do that, but it is pretty important, especially when you're initially solving systems of 3 equations with 3 variables, just because the process can be pretty messy and it's very easy to make one tiny mistake along the way that throws off all of your answers. So by checking in the original equations, you're going to make sure that you actually did solve it correctly. Okay, so we'll do a couple examples together. This first one, we're just going to go step by step by step. Okay, so first, write down the system. We have 3 equations here with 3 variables. Notice our x's are aligned, our y's are aligned, our z's are aligned, and our constants on the outside. Okay, so step number 1, we said we reduce the system to 2 equations with 2 variables, which means we need to figure out which of the variables is easiest to eliminate. Okay, so I kind of just take a quick glance. I have an x, I have a 3x, I have a 2x. None of those are going to eliminate very quickly. Look at the y's, you have 4y, 2y, negative 3y, same with those. But then when I look at the z's, I have a negative z and a positive z. I know that those can eliminate. And then in the third equation, I have a 2z, and that's going to be a lot easier to get to versus one of these other numbers. Okay, so I'm going to kind of make a note to the side for myself, and I would highly suggest doing this as well when you're solving these problems, that I am going to try to eliminate z. Now, the way that I do that is, like we said in the previous slide, I have to take 2 different pairs of equations and do elimination method to eliminate z. Okay, so another quick just tip that I have for you guys is to label these equation number 1, equation number 2, equation number 3, so that you're not getting lost in all of your work. So the first and easiest 2 equations to take to eliminate z, I would say, would be equation number 1 and 2, because I automatically already have a negative z and a positive z here that will eliminate. So that's what I've written over to the side here. Okay, you pick a pair of those equations. Now, I don't have to manipulate anything here. I can just go ahead and add them and then, like I said, eliminate these 2. So I get x plus 3x, which is 4x, 4y plus 2y, which is 6y. The negative z and the positive z eliminate, like we already said, and then 20 plus 8 is 28. Okay, so that's the goal, is to get an equation now with just 2 variables. Now, I can't really do anything with this unless I have another equation that also just has 2 variables. And so the way that I'm going to do that is now by using a different set of 2 equations up here. So I've already used 1 and 2, so now I either need to use 1 and 3 or 2 and 3 and combine those. Now, it really does not matter which ones you want to choose. I would just choose, whichever ones look a little bit easier for you. So let's see, I'm going to choose 1 and 3 here. This one has a negative z already, and then this one has a positive, and so if I multiply this top one by 2, I'm going to be able to get a negative 2z, which will eliminate with this bottom one here. Okay, so that's kind of my next goal. So I have 1 and 3 here. I'll circle these. But like I said, if I wanted to choose 2 and 3, that's totally fine. Okay, and I'm going to multiply 1 by a positive 2. And then 3, I'll carry down here. Okay, now I always like to just write this out as is. That way I can see where did I start. So if I get lost in my work or I mess something up, I can very quickly and easily go back to just check on things. Okay, so I'm going to distribute this 2. I get 2x plus 8y minus 2z equals 40. Okay, then carry down or rewrite my third equation like I already had it. And now my negative 2z and the positive 2z, those are going to eliminate. Okay, so then I add down, I get 4x, 8y minus 3y is 5y, and then 40 minus 16 is 24. Okay, so here was my goal for step number 1. Yes, this is all step number 1. And honestly, this step is usually the hardest. So I reduce the system to 2 equations with 2 variables, and they need to have the same variables. So notice both of these have an x and a y and x and a y. If they have different variables, that's not going to do you any good, because then when you try to go to step number 2 to use elimination method on these 2 equations, you're not going to be able to eliminate the variable if they don't have common variables. Okay, so usually what I do at this step is now I like put a star by these new 2 equations that I'm going to be using. Again, just because that can make my life a little bit easier when I go to do step number 2. So step number 2, we've got these same equations that I just wrote right here. This one's the first one, or the second one, and then this one was that first one. So step number 2, we solve the resulting system of 2 equations with 2 variables, and we do that like we would do normally with elimination method. So I look to see, can I automatically eliminate any of my variables? Well, I do have a 4x and a 4x, but one of them needs to be opposite sign or negative. So I'm going to go ahead and just multiply this second one by a negative 1. It really does not matter if you want to multiply the top one by that. I just always like to do the second one so that it looks like I'm subtracting. Okay, so I get negative 4x minus 5y equals negative 24. Just make sure you change all of those signs. So now I can eliminate, and I get 6y minus 5y, which is just a 1y. 28 minus 24 is 4. So step number 2 is going to result in you having one of your answers or one of your variables solved for. So that's y equals 4. Okay, now step number 3, I'm going to go back to one of these original equations that I just used because these only have the 2 variables. And since I have what y is, I could plug y in for either one of these and then solve for the remaining variable, which is x. You don't want to go back to one of the original equations with 3 variables because you will not be able to solve for one of the other variables when you still have 2 of them. Okay, so like I said, we've got y equals 4. We can use either one of these equations to plug it back in for. And so let's just say I choose the top equation here. I'm going to plug that in, 4x plus 6 times 4 equals 28. And again, what I really like to do is color coordinate so that I can kind of see on my paper just a trail of what I'm doing where and what equation is coming from where. So if I was using colors like I am here, I would just put a star that's pink right next to this one so I can see what equation I plugged it into. Okay, so I get 4x plus 24 equals 28. I'm going to subtract the 24 from both sides. 4x then equals 4. Divide both sides by 4, and I get x equals 1. Okay, so here's my second variable that I've solved for. So I'm almost done. I have y, I have x. Now I'm done with these 2 equations, right? Because they don't have a z in them, so they're of no use to me anymore when I'm trying to solve for my third variable, which is z. So step number 4, I take the x value that I found, which we just said is 1, the y value, which is 4, and I plug that back into one of the original equations. My original equations are up here in the top corner, okay? They're rewritten for you. And just like before, you can pick any one of these equations. I always just pick the one with, the smallest numbers or that looks a little bit easier to work with. So I'm going to choose the top one because it just has the smallest numbers. So we're going to plug in 4 for y, 1 for x, and then that way we can solve for z. So I get 1 plus 4 times 4 minus z equals 20. This becomes 1 plus 16, and that becomes 17. So subtract 17 from both sides. I get negative z equals 3, and negative z is the same thing as having a negative 1 out in front of that z. So I can divide both sides by negative 1, and I get z equals 3, which is my third variable. Okay, so now the proposed solution that I have is combining all 3 of these. Let me just have a different color here. So I have 1 for x, comma, 4 for y, comma, 3 for z. I'll color coordinate this for you guys too. Okay, and the reason I say proposed solution is just because you do want to make sure, especially since you just did a whole lot of work, and it can be, again, easy to mess up, that you go back and you double check your solution. So this is step number 5. Again, we're not always going to ask you to do this, but at least initially it's a good practice to get into. So if we are checking this solution, again, we're going to plug in these values for our x's, our y's, and our z's. So we'll plug in 1. Whoopsies, I used a different color, but you know what? That's okay. 1 for x, 4 for y, and then negative 3 for all of my z's. And we will check to see, does this actually work? Okay, so 1 plus 4 times 4 minus negative 3. Make sure you put that in parentheses because it's a minus z, and z is already negative. So I don't want to miss that second negative. I'm going to see, does that equal 20? Well, this becomes 1 plus 16, and then minus negative becomes a positive as well. So 1 plus 16 is 17, plus 3 is 20. That does, in fact, check out. Okay, so that one works. Let's check the next one. So 3 times 1 plus 2 times 4 minus, or nope, that's a plus, negative 3. Does this, in fact, equal 8? Yep, we get 2 times 4 is 8. So 3 minus 3 right here, that's going to give me 0. And then I'm just left with 8. That does equal the right side. So that one checks out. Okay, then the last one here, plug these in again. I get 2 minus 12 minus 6. 2 minus 12 is negative 10. Negative 10 minus 6 is negative 16. So that does, in fact, check out as well. Okay, so remember, the solution only works and satisfies all of the equations if it works in every single one. All right, let's do another example here, just because, again, this process is pretty long. So you can go ahead and write down these equations. I also have them written on a separate sheet of paper here, just because this is going to require a little bit of work. Okay, so after you've done that, and feel free, you can pause the video if I'm going too quickly, we're going to try to figure out which variable is going to be easiest to eliminate. So x's, I have x, 5x, y's, I have y, negative y, and then z's, I have z, 5z, and z. So I'm going to say the y's look easiest because I have positive y's and a negative y, and so those look like they're going to be pretty simple to eliminate without having to multiply by anything. That does not always happen, that's not always the case, but in this case, it works out great for us, okay? So I'm going to label equation 1, 2, and 3. So first, I'll just start with equation 1 and 2 because I already have a positive y and a negative y, and so those are going to very quickly eliminate. Again, over to the side, make yourself a note of what variable you are trying to eliminate, just because that can kind of help you so you don't get lost in all of the work. So here's equation 1, here's equation 2. I do not have to multiply by anything in order for these to cancel. Okay, so the y and the negative y, when I add them, those eliminate. So I get 2x plus 6z equals 14. Okay, so I used equation 1 and 2. Now I can use equation 3 because I have not used that yet. And if I look to see, do I want to use 1 or 2 with that? Well, 2 already has a negative here. Okay, if I wanted to use example or equation 1, that's totally fine too. I just have to multiply that by a negative number. So instead of that, let's just use equations 2 and 3 because that makes our lives a little bit easier. Easier is the name of the game, especially when it comes to this process. Okay, so again, my y's are going to eliminate really nicely here. Go ahead and add down. So we get 6x plus 6z equals negative 6. And then, like I did before, I'm going to just put a star with a different color by these two specific equations because these are the ones that I'm going to use to now eliminate. Okay, actually use a different color so we don't get that confused with the blue. All right, make sure before you move on that you have the same variables for both. So we have x's and z's, x's and z's. Yep, we're good. All right, now we take those two equations and we're going to eliminate with those. So let's go ahead and write them down here. All right, and we see, can we eliminate pretty easily here? Well, I have a 6e and a 6e, and so the way that I'm going to do this is by multiplying one of the equations by a negative so that those can very quickly eliminate. All right, so let's multiply the second one by a negative. So I'm going to just write this over to the side. Top one stays the same. We got negative here, and a positive on this side. Okay, now I have a positive 6e and a negative 6e. Those are going to eliminate. 2x minus the 4x, or sorry, 2x minus 6x is minus 4x, and then 14 plus 6 is 20. So now I'm able to solve for my first variable, which is negative 5. Okay, so I have that one solved for. All right, so next step, we back substitute this in for one of the original equations that I was just using in two variables. So either this one here or this one here. I'm going to use the top equation just because that one looks a little bit easier to use. Okay, so I'm going to plug it in here, and again, I'm just going to star this down here so I know which equation I was plugging it back into. 2 times negative 5 plus 6z equals 14. So this gives me negative 10 plus 6z equals 14. Continue solving. So at least all of this is just a bunch of algebra. I get 24, divide by 6. I get z equals 4. Okay, great. I'm almost done. So I have two of my three variables. I have x and I have z. So now I am done with these two equations that just have two variables because there's no y in there and I need to find a y. So in order to do that, I now back substitute both of these solutions, x and z, into one of the original equations up top. Okay, so let's use a different color here. I'll use orange because I have not used that one yet. I'm just going to use this top equation, the first one, because that one looks easiest and has the smallest numbers. Okay, so I'll plug in x, which is negative 5, plus y, we don't know that, plus z, which is 4, and that equals 1. And now I'm going to solve for y. So negative 5 plus y plus 4 equals 1. Negative 5 plus 4, I'm going to combine. That gives me negative 1 plus y. Add 1 to both sides. We get y equals 2. Okay, and now we have our solution. So negative 5, comma 2, comma 4. Or that's our proposed solution. Okay. So then we would go ahead and go on to actually check that if we were being asked to do so. Example number 2, this is just another example of checking if an ordered triple is the solution to the system. I'm going to skip this because if you have already done that the last couple examples, you should be okay. It's the same exact process. You would plug in the -1 for the x's here, you would plug in the 5 for the y's here, and you'd plug in the 1 for the z's. And then this one, if you do want to actually practice this just to confirm that you're understanding it, this one actually does check out. It is going to end up being a solution to the system. So feel free, you can work that out on your own if you'd like. Okay, the last problem that we're going to do is an application problem because, again, oftentimes with systems of equations, including ones and three variables, this can be really, really helpful when we have application problems or word problems. So let's go ahead and read it. It says the sum of three numbers is -6. The second number is subtracted, or if the second number is subtracted from the sum of the first and third numbers, the result is -4. And if the third number is subtracted from the sum of the first and second numbers, the result is -2. Find the three numbers. Okay, so we are given a task here is to find the three numbers. Those are our unknowns, or those are our variables. And so that would be the first thing that we would define here. Now, the nice thing is that we're already given a hint. So we're just going to let x represent the first number, y will represent the second number, and z will represent the third number. Okay, then we need to go back through and kind of sift through all of these statements we are given, or information, just to figure out how are we going to write equations from this. We have three variables, and we are given three different pieces of information here, one in each sentence, and so likely that's how we're going to know that we have three equations to solve. So the sum of the three numbers is -6. That's the first piece of information that we are given. So that can correlate to our first equation. Okay, sum means adding. So if we know the three numbers are x, y, and z, that means when we add x plus y plus z, we get -6. Okay, so that's our first equation. The second statement tells us if the second number, so y, is subtracted from the sum, so addition, of the first and third number, so first and third would be x and y, then the result is -4. Okay, so that means if we take x and add it to y, that sum, and then we subtract the second number, or sorry, that should be x plus z, first and third. Then we subtract the second number y from it, we get -4. That's going to be our second equation. Okay, and then finally, our third equation. So if the third number, which is z, is subtracted from the sum of the first and the second number, the result is -2. So the sum of the first and second number would be x plus y. And then if we subtract z, the third number, from it, we have -2. Okay, so here is our system of three equations with three variables. Now, before I go on to solve these, I do want to rearrange them a little bit just to make sure that I have the x's, the y's, and the z's all in the correct order and placement. Okay, so in the first equation, I'm good to go. The second, or the last equation, I'm good to go as well because I have x, y, and then z. It's the second equation that I need to rearrange a little bit. So if I get rid of these parentheses, I'm just going to flip-flop the location for the y and the z so that I get x minus y plus z equals -4. And then I can rewrite my other two equations here. So now everything looks good to go. We have all of our variables and our constants aligned. Okay, so for application problems, that's going to be the additional step, is having to actually set up your three equations with three different variables and making sure you define them properly. All right, so now the solving process is the exact same as what we have done before. So we're going to label these equation 1, equation 2, equation 3. We're going to look to see which variable can most easily be eliminated from all three equations. Now, this one, really, we could go with any of them because we have and let's see, a different color. We have x, x, x. We have a y, a negative y, and a positive y. And then for the third one, we have z, z, and negative z. Okay, so really any of these are going to be great options because they don't have constants in front of them. And some of them are already negative, some of them are already positive. So I'm just going to choose the middle set, the y's, to eliminate, just because the middle is already a negative y and the other two are positives. Again, though, if you choose to eliminate a different variable, that is totally fine. So if we eliminate y, Then let's just start with our first and our second equation, because if I look here, I already have a positive y and a negative y. So I'll carry these down here, 1 and 2. Okay, we have x plus y plus z equals -6, and then x minus y plus z equals -4. So the y and the negative y is what I am eliminating here. So I get 2x plus 2z equals -10. Okay, so I've already used 1 and 2. Now I'm going to use 3, obviously, and if I look at equation number 3, I have a positive y here, and so the easiest one to use with this one, again, would be the second equation. Otherwise, if I use the first one, I just have to multiply that by a negative. Okay, so we're going to use equations 2 and 3. So x minus y plus z equals -4, and then x plus y minus z equals -2. Okay, so my negative y and y, those will eliminate. I get 2x. And then, hey, would you look at this? This just happened accidentally. The z and the minus z, they also eliminate. And so I'm only left with my one variable of x, okay? So 2x equals -6. So I'm going to go ahead and continue with this, and I get x equals -3. So sometimes you're going to notice this happens where multiple of your variables will cancel at one time, and then it actually makes the process a little bit easier because you do not have to go through that additional step of taking your two equations and two variables and eliminating them. Okay, so I have x equals -3. I'm going to go ahead and plug this in. Let me use green color here. Plug this in for this equation in two variables, okay, because I need to solve for another variable, and this is going to allow me, if I plug this in to the x position, I can then solve for z. Okay, so I take this equation down here, 2 times the x value we just found, minus or plus 2z equals -10. So I get -6 plus 2z equals -10. Go ahead and solve. So I get -4 here, divide by 2. So I get z equals -2. Okay, so now I have two of my variables solved for, which is great. Okay, and then I'm going to plug those back in to one of the original equations up here to solve for the third. And here it doesn't really matter. They all are going to be pretty equally easy to plug into. So let's just say I use the first equation just for simplicity's sake. Okay, so let's plug in x is -3 plus, we don't know y yet, plus z we said was -2. And I'll color coordinate this for you. Okay, and then all of that should give me a -6. So then I combine -3 minus 2 is -5. And then I add 5 to both sides, and I get y equals -1. Okay, and so now, let me use a different color here. I've got my ordered triple, so x, comma, y, comma, z. That is my solution. Okay, and we're not going to check here, but again, you could plug these back into all three of your original equations and just make sure that they do work. All right, the last thing I want to just talk about really quickly is, what does this look like from a graphical standpoint? Now, we're not going to have you graph these systems of three variables and three equations yet, but this is something that I just want you guys to be exposed to a little bit. So we talked about, a graph of a 3D plane. So that has an x, a y, and a z axis. And so it is going to look like, instead of just a coordinate grid, it's going to look like a plane. Okay, so when you find the solution then to a system with three variables and three equations, the answer, instead of being an intersection point, it is an intersection of three separate planes. Okay, so the possibilities of these are shown here on this next slide. Again, these look kind of complicated, but you notice you have three different planes. So plane number 1 is the purple one, plane number 3 is the orange, plane number 2 is the blue. And so that point that you just found, the ordered triple, that is the intersection point of those three planes. Okay, up here, same thing. Here, this would be no solution if you have all three being parallel planes. This right here would be an example if you have infinitely many solutions. So if the planes intersect in a perfect line like this, or if all of the planes are identical, that would also give you infinitely many solutions here. Now, in this second example, this is an example with no solution because the three planes each intersect another at no common point. So they intersect, but at different points. Not all three you see will intersect at one point because this is where 1 and 2 intersect. This is where 2 and 3 intersect. This is where 1 and 3 intersect. Again, you do not have to know this yet, but this is just kind of good exposure for you guys to see for future math classes. Okay? All right, so today's homework is the 6.3 worksheet.